Hello everyone and welcome to the introductory video on the data structure linked lists. In this video we are going to talk about what linked lists are, why, where and how they are implemented. So why and where they are used and how they are implemented. So let's begin with the what. What is a linked list? Well, a linked list is a data structure that stores the data and uh, all the sets of data are stored in nodes and they point to each other. So if I were to draw to make things more clear, this is a node which is pointing to another node. So it will be something like this. These are the nodes. So this is a node and this is pointing to another node. And in this way, this can go on for any number of elements that you want to store in the data structure, right? It is a linear data structure, and therefore the the node on the front is called the head, and the node at the very bottom or at the very tail of the data structure is called tail. Now it can store data, and these values are data. So if we do not have to talk about the coding aspect, the linked list on paper theoretically looks like this. It is just a node, nodes interacting or interconnected to each other by pointing to each other in a unidirection. So this is what a linked list is. Now, why are they needed and why not arrays? So in an array, what happens is if I were to store the same data 0, 1, 2, 3 in an array, I would have stored 0, 1, 2 and 3. And what would have happened is on the memory grid, it's very something very messy structure on the memory. A random location would have been selected, and then the first element would have been inserted there, and then this is a 4 element array. What array would have done is on the memory grid, it would have taken 4 memory units in continuation and started the array as 0, 1, 2, 3. So the key thing in arrays is that the adjacent elements are also adjacent at adjacent locations on the memory, whereas on a linked list what happens is in the memory grid, 0 could have been here, 1 could have been here, 2 could have been here, 3 could have been here, and each of them have a unique and a very random location assigned to them, and each of them is has a reference of where the next element is, so it can basically point to the next element using the it's basically these are the friends who have the contact and location of other friends where they live on the memory, and they can direct like for the next friend you go there. And over here what is happening is all the friends have brought the house in the linear fashion side by side. Here what happened is all the friends living in the memory colony have houses at very separate different locations, but everyone has the contact of the immediate right neighbor. Now that was a very silly analogy, but I hope it makes sense and helps vividly imagine and understand the things, how the array and linked lists are different in this aspect. Now, another amazing thing about arrays and linked lists is since arrays are in a very linear fashion, what happens is when you pop from the array. So let's say I want to pop this element out of the array. What will happen is one will not just be popped out of the array, but two will take place of one and three will take place of two. What I am saying is on the memory grid, when you pop out the one, so when you pop out this one, What happens is there is a vacancy in this space. An array is a very continuous data structure. It does not allow vacancies. So what automatically happens is 2 is shifted in place of that vacant place. The origin, the left head, the main address of the array never changes. And then when 2 is shifted to the place of 1, a vacant space or vacant memory location is created in place of 2, and therefore 3 moves towards left to make sure that it fills it up. Now, in terms of time complexity, it is very expensive. Not very expensive, but yes, it's expensive because just to pop one element, O of n operations at worst case can take place. If the popping element is the very first element, then O of n operations will take place. First of all, this will be popped, then everyone shifts towards left, and that is O of n. However, that is not the case in linked lists, and that is a very strong advantage point of using the linked list. What happens is if in a linked list, like over here, you want to, I'll just change the color. What happens is in the linked list, what if you want to just focusing on the first element, if you want to remove this element, what you do is you just shift your head pointer to here and you break this connection, and then this is now the new head, and everything is uh, taken care of in just O of 1, not O of n. Nothing needs to shift left or right because there was never a linear locations in the grid at all. So in linked list, you simply can manipulate the pointers, and that saves a lot of time. But linked list have its negative points as well, because in arrays you can access an element, let's say ARR of 2, that is this element. In O of 1 you can directly access an element at any index in O of 1, but in linked list you always have to start from head. You always start from head and you go down the line using the pointers. You cannot directly access the elements. You can't directly jump to O of I mean the second element of, or the 22nd element of the linked list. In fact, you could have done that on the array, but in linked list you have to start from head and then go 22 times to the next element, and then you will be at that position. That means it takes O of n times at worst case to O of n time complexity to uh, access an element. So where can we? So we now have have an understanding of what linked list is. At least on the paper, we know what a linked list data structure is. Forget about the coding aspect. Then we also understand why they are needed. It's because the insertion and deletion operations on the either ends of the linked list is very cheap, whereas on an array it is expensive. So that is a very plus point that we saw on the linked list, and we also understood that linked list is scattered, whereas the array is very rigid in its structure, and every element needs to be side by side. Now let's talk about where are linked lists used, and then we can also check out how this data structure came into existence from the coding point of view. So where have I seen a linked list being used? So it has to be a queue. So queue is a first in first out data structure. What happens is whatever you insert, let's say I insert 1 2 3, the insert operation takes place on the tail side, so I'll call this tail side, whereas the popping operation takes place on the head side, right? Head side. So If I were to implement this using an array, for every pop, let's say this is a 1,000 element long queue. So if I were to pop from the front of the queue using an array, what will happen is every pop operation will take thousands of operations uh, for just simple removal of the first element from the data structure. But if I do it using a linked list, what will happen is I can do it in O of 1 time complexity. So what will happen is to be more graphical, when I pop this out, every element in array has to shift one element towards its left, and that is expensive. But in the linked list, what will happen is we simply break this connection, and this is our head pointer. We update the head pointer from here to here, and that's it, O of 1. And now this is the linked list with this as head. So I'm writing it again, so no need. With this as our head, tail remains the same, and we did it in just O of 1, and this took us O of 1,000, that is n, right? So that is the plus point of a queue. You can pop from both the sides without any time, with a very less time complexity. And it's not just about popping it, you can in fact insert new elements on both ends very easily. So if I were to insert an element, so let's remove all of it and redo the insertion operation. So if I were to insert an element, let's say 0 to this queue, what I will do is I will create a node with value 0 and point it to the head of my linked list, and then I will update my head from 1 to 0. So I will earlier this was my head, and I created a node here. I initialized it to 0, store 0 value. I made it point to the head of the linked list, and then I updated my head from 1 to 0, and now I have a new data structure. I have that data structure with starting with 0. So this was done in O of 1 because I just had to create this and point it to that. But in an array, what I will have to do is I will have to it's going to be messy. What will happen is I will insert 0, so 0 will come in here, and every element shifts towards right. There is no way that I insert 0 here and make an array go like this. No, the first element memory location is fixed in an array. So if I have to enter 0 as the first element, what will happen is 0 will take place of 1, and 1 will take place of 2, and 2 will take place of 3, and that will go on till the end of the array. And if it is a very long array, it is going to be an expensive operation, and you don't want to do it. So if there are data structure like queue where you have to pop from the front on a regular basis, queue for that data structure, linked list is very much advisable. And in fact, the queue data structures or queue libraries that you use in your programming languages use linked lists instead of arrays. That is why they are faster and more efficient. Now we have the understanding of where. So now let's have a look at how these linked lists are created. So now we are going to consider how. So basically a linked list is not just a data, it is a data, and here it is a pointer. Pointer is nothing but the memory. It is pointing to the memory location of another node, right? This together is a node. So what I will do is I will create a class node, and in this I will make a constructor. It will take value as an argument. It will set its object val as the val. So if I make node 0, what will happen is I will create a node with data 0 and self.next equal to none. So When I call a class node 0, what happens is I created a node 0 and that points to none. That is, it points to nothing. What I can do then is, so I call this n, small n, as node 0, and then what I can do is n dot next is equal to node 1. So now these two together have created a linked list, and we have to, in fact, now to name the head and to keep a reference of head and tails is another task. But just these two lines and this class over here have by themselves created the linked list, a small linked list data structure. Let's see. So n is a node. So n is a node, and it has a value of 0, and it points to nothing. Okay, but then and dot next, I'm updating this pointing variable. So now this is going to point to what? It is going to point to a node, an object, a node. So this is our object node. It has a value of 1, and this 1 has a pointer that is by initialization of the constructor is at the point none. That is, it is not pointing to anything. But so if it is not pointing to anything, I'll just remove the arrow of pointer, so it is none. So it's stand end here. So by themselves, this is a small linked list of 2 elements. And as you could have guessed, we can use a while loop or any loop to make this data structure, make a program to uh, make an element data structure. We do not have to do and dot next dot next. It's just we have to update that n equals to n dot next and put everything in a while loop, and that will take care of itself, and this loop will be go on for a long time. So 3 lines of code in a loop will create the data structure. Yes, it takes more memory than the array, and the trade-off is you can insert and delete at the ends of the data structure in just O of 1 time complexity. It has its practical implications as well. It is used in Q and very different um, practical applications on your desktop. Just Google the applications of linked lists and you'll be able to see some of the very familiar terms. So with this we are done. Next up we will try to code this on our editor and test it.